Okay, good morning, and sorry for the delay. So, yeah, we talked already quite a few times about the keyword machine learning, some buzzwords found. So this lecture, or yeah, half an hour here that I prepared, I will talk about learning representations, learning embeddings, learning features. These are all the same things, right? There are many names for an old concept. And I realized a bit that we have a very diverse crowd, which is excellent. So I tried to design this lecture in a way that everyone could get something out of it. So yeah, and I gave it the title From Feature Engineering Towards Pretext Task Engineering. And I will show you in a bit what I mean with that. But let's start maybe by first having a quick look at what is this deep learning. So if you look at a more classical machine learning approach, we would have our raw data. This could be satellite observations. And then back in the days, or maybe still today, we would design some clever features by hand. And then we would pass that to a machine learning model. It could be a linear classifier, could be an SVM, a random forest, etc. Now, this to design basically very good features. In the era of end-to-end deep learning, these two steps, the feature extraction and the classification or regression, they are somehow merged. And we want to learn this end-to-end, such that both stages can also talk to each other and cooperate. So we want to learn these features directly from the data without engineering those features. And I mentioned that already. So there are many names. Please don't get confused or scared. Features, representations, embeddings. I would say these are the same things. It depends a bit, yeah, with whom you're talking. But yeah, I typically call it features or representations. Nowadays, if you want to sell it as a product, you would call it embeddings. So that's a bit, yeah, adds to the confusion maybe, but it should not. So what do I mean with this from feature engineering towards pretext task engineering? So these could be some handcrafted features that worked well in the past. So some Hawk-like features that describe an image. Or then in Earth observation, we could think of the NDVI as some clever feature that is more predictive for vegetation characteristics than the raw bands itself. Then we came into the neural network game with the convolutional neural networks. Today we also have transformers, etc. So there was a lot of engineering in the architecture itself. So over a few years, people were trying to engineer better neural network architecture that can learn better features. And now today, I think there's not so much engineering in the architecture anymore, but there still is. But what people started to do is to engineer proxy tasks, like alternative training tasks, pre-training tasks. And here I just have a few examples. For instance, it has been shown that asking a network by how many degrees this dog image was rotated, I think we all can also estimate that or give a guess, 90 degrees, that such a task can actually learn meaningful semantic features from the image, because there's a natural structure that we typically observe dogs, following gravitation, and we take ground level images in a structured way. We very rarely take a picture like that. Or things like solving a jigsaw puzzle, like asking a neural network, oh, how should we actually fix this back into the image? Or colorization, asking a neural network to go from a grayscale image to colors. All this requires to interpret the image somehow semantically. And like by learning these intermediate representations, one can show that this then actually goes and generalize to some downstream tasks that we actually care about, because we don't care about these pretext tasks. Okay. So just a very brief recap when we talk about supervised learning, that is, I guess, the most successful setup. If we have a lot of training data available, we can say, oh, let's just use supervised deep learning, and then we probably get a pretty good result. The key here is that we have to define a loss function based on our labeled data. So in this case, y. And this is where the magic will happen. And we can tackle many tasks, from regression to classification tasks. So at the heart, or at the core of all of this, I would say, is a linear classifier. You find that in many neural networks at different stages, you will have something that looks like a linear classifier or a linear projection. And so this is not much more than learning basically these linear projection and then a bias term. And so this is fine for linear problems, right? There's nothing surprising here. But the big question is, what do we do when we have a nonlinear problem and our linear classifier will not help us to solve the problem? And the idea is, oh, can we learn to project? So let's take this spiral data set as a problem. You see that the linear decision boundary cannot separate these two classes, red and blue, with a linear line, right? So the question is, can we transform the input data into a different space, into a different representation, where it actually becomes possible to draw a linear line and separate the data? So for me, that was several years ago, I think, a click moment when I read this sentence, that the point of deep learning is basically to learn how to project your raw data into a new space such that it becomes linearly separable. And for me, that was very useful to understand intuitively what is actually going on there. So how to train such a neural network? This is all recap, I guess, but yeah, we need this loss function, and we will typically do something like gradient descent, right? So we will differentiate the neural network, the function that maps the input to the output, and then we will look at this loss landscape. Here's a 2D visualization of it. Like if you think of these two parameters, a very simple model, just two parameters, and then the y-axis here would be the loss, the cost. So what parameters should I choose to minimize that loss, right? That's the question, and how to find that. And typically we randomly initialize these parameters because we don't know what they are. And this could put you maybe on the spot here. And then you will try to find basically, oh, how can I go from this place to a local minima, or ideally the global minima, to then get a good solution. And here, this is just an illustration of the problem. If you think of the loss as a landscape, like our loss does not have the full picture of the landscape. It cannot look into the distance and say, oh, I see a local minima over there, and I have to go this way. We only see in the neighborhood, basically. So you can think of it like this little figure here that blindly tries to figure out, oh, which is the steepest way to go my next step, and then I will go that step. And then this is the iterative process that we use to optimize these neural networks. And as I mentioned, this whole process leads to good results if we have a lot of training data, but in many applications, we do not have so much training data. So the question is, what about the small training data sets, and what can we use here? And I'm all building up towards the keyword self-supervised learning, but there is a lot of techniques out there with different names, and they're all somehow related. So you might have heard of transfer learning, where the idea would be that we pre-train a model on some task A, for which we have a lot of data, a lot of training data. But the ultimate goal would be to solve actually task B. So we would take that pre-trained model and then transfer it and only fine-tune it, for instance, with very little training data from the task B that we care about. And then there are things like multitask learning, where we could start to add like additional tasks with more data on the side, or then concepts like weekly supervised learning, where we might just have a good approximate label, right? Not the perfect gold standard label, but we have a lot of weak labels. So in a classification problem, this could be a coarser category. In a regression problem, it could also be, we might get reference data at a much coarser spatial resolution than what we are actually interested in. So there are many ways that fall into these different concepts. And I think all of it is somewhat or builds up towards this so-called self-supervised learning, where we define these proxy tasks to learn representations. Okay, so why should this transfer learning actually work? And envision, like you might have seen these illustrations, visualizations from features learned by convolutional neural networks, for instance. So some of these learned features are very generic. They would work on any kind of images, any kind of image domain. And some features are more specialized, more focused on the task on which the network was actually trained on. In this case, it's some face application. And we see that some of these features, if it really learned to detect eyes, that might not be the best to transfer to Earth observation data. But so how to do this transfer learning in practice on Earth observation data? So this was a very famous example, I think, or successful example, where the goal was to map some poverty index. And the data for this task was very scarce. But however, what is abundant or like globally available are these so-called nighttime images. And instead of using these nighttime images as an input feature, one can think of it as a good proxy task to predict basically the nighttime lights from optical images. And then after pre-training on such a task, one can transfer to the poverty mapping tasks. Okay, so this just a bit as an introduction to self-supervised learning. And if you look into the computer vision domain, this is very much at the core of many of these self-supervised learning approaches, contrastive learning approaches. So the idea here is to engineer basically positive pairs. So what we would want to do, so X is our input data. This could be just a raw image observation. It does not have any label. And what we would do is we would take this image and create two views out of it by applying two random augmentations. So here are a bunch of examples how such an augmentation could look like. If that on the top left is our original image, these are all kind of valid positives where we would still say, oh, this is still a dog. So the network would be trained to basically learn a feature space after encoding it with F here. That would be our encoder. We would get a representation. And in this representation, a positive pair from these artificial augmentations should be close together. So it should be embedded in the space close together. And everything else that is a negative pair should be pushed away. So by doing that, one can yield very good like representations, especially on data sets that are kind of object-centric. So there's a lot of research going on ImageNet, which is, I would say, an object-centric data set where there's always some kind of object in focus or in the center of the image. And the reason why this works so well for object-centric images is because there we know somehow how to engineer these augmentations. Okay, so a counterexample where such a technique does not really work so well, we can already find it in a ground level image domain. So some of you might have heard of iNaturalist, the citizen science platform, where you can upload your observations that you made on a hike, and then the community then labels it down to the species level and even more attributes. So there are maybe some of these object-centric images. I would still call these example object-centric, but very often the bird of interest is just very small in the image, and there's so much like just background and scene in the image. So a random crop, like it's proposed here, like for instance, cropping into the image, cropping away the surrounding, could actually crop away the object of interest. And then this is not really a positive pair anymore. Oh. And so the whole message that I want to convey here, this was a nice study by Van Horn et al. I can recommend reading this paper. So they show that this is a bit a complicated graph to read, but the main message was that this self-supervised pre-training scheme, relying on these augmentations, does not even generalize to a ground level, to a different ground level domain like these iNaturalist images. So we need to, I guess, come up with better augmentations depending on the task that actually, yeah, do not destroy the semantics. Okay, but we are here to learn a bit about Earth observation data. And because how does this then even translate to Earth observation data if it does not even, work on a different ground level domain? And there's a lot of research going on. So this is my attempt of mapping the recent papers and into a 2D space. But I will try to give you a bit of hints and structure how to read this. So I think what all these papers do is they explore 3 major aspects of Earth observation data. So we can try to find some clusters that make use of geolocation, make use of time, or make use of different modalities. So maybe now this looks a bit less arbitrary. And today I will mainly talk about some earlier works that showed some interesting Earth observation specific pre-training ideas. And I think still today, many of the follow-up works are based on these ideas. But this map, or this, it's not a list, right? But it's very incomplete. So as we speak, there are probably 3, 4, 5 new archive papers popping up. So it's a very active space right now. So it's quite exciting. Okay, let's first talk about geolocation or geolocalization. So first of all, how is that used in computer vision today? Geolocation can used as a prior, can be used to condition your model. For instance, in fine-grained like species distribution mapping, it has been used to learn a geoprior. So if 2 things look very similar in the image, in its appearance, the geolocation could actually help to separate that out. And an alternative way of using geolocation is to use it as a target. So to basically take an optical image and then ask a model to localize it, to geolocalize it, to put it on the map, basically. And this is more towards how it is used also in pre-training. So in this particular study, the end goal was to localize it. But an interesting illustration here, also from that paper, is that what happens when you ask a model to localize an image just by looking at the image. And they were trying to visualize the importance of different regions in the image by basically hiding or masking out a specific pixel in the image, and then see how the confidence of the network react. These are different examples. I don't think they are perfect, but at least they give some hints. For instance, here, the last example is from Shanghai. And they say, for instance, these palm trees, they are not so typical for this region. So if we mask them out, the confidence of the model actually goes up. Okay, that is maybe convincing, maybe not, but I think we are all used to look at satellite images. I assume so. And there's a little game. So ESA plays that quite, or I'm not sure if they still play it on social media. They post these images and ask their followers or the community, where on Earth is that? So it's a GeoGuessr game, right? And maybe some of you can know it. I don't know. I'm not sure if how we could do that, but maybe let's just do it for the first one. Who thinks that this is in Bolivia? Hands up. Who thinks it's in Florida? It's a good amount. And the last option is Peru. Your hands. Okay, so seems like we are quite good at it, huh? So there are visual features that tell us, I probably know that place. We could play it for the other ones, but I want to speed it up a bit. So the second one is from Bolivia, and now, no surprise, the last one is from Peru. So somehow we humans can extract semantics, and we want to use that also when we train neural networks. Okay, so let's talk about some pre-training approaches that use geolocation and time. So there was this paper, I think it's one of the first ones that showed this idea, geography-aware self-supervised learning, GASSL. And the key idea was that, let's move away from these weird artificial augmentations and use something more realistic. And one thing, obviously, is that we can get a time series of a location, and we get naturally augmented data. So we get natural augmentations that are realistic. And the other idea, so what do they do then with this time series? So instead of, this is the same concept as I explained before, where we would take an image and we would like to have two different views out of it to then learn a representation in which positive pairs are close together. So what they do is they use simply images from two different time steps and tell the model, oh, that's the same thing. It should be close in feature space. And on top of that, they also use like the geolocalization task to then learn representations on top. So this was kind of promising. They showed decent performance improvement. The only thing that somehow didn't work yet, or what that was surprising, is here there's like different ablations. So TP means for temporal positives. So what they couldn't really get to work is that the temporal positives and the geolocalization, that these two tasks, they should be somehow complementary, but in these results they were not. And then following on this, there was a paper called Seasonal Contrast. And I think it's a bit more, let's say, slightly more complex approach. But the key idea here was that this temporal, like the model before, maybe go back to that slide briefly. This model basically learns to be invariant to time, right? We tell the model these two different time steps, they look different, but they are the same semantic object. So this might be fine for static tasks, right, where we do not assume any change over time. But when it comes to change detection and so on, that's probably not a good idea if we pre-train on such a pretext task. Then we would actually prefer to have a model that is sensitive to changes over time. And that is, I think, what SECO, the seasonal contrast paper, mainly tried to tackle. And they approach this, again, by sampling positives also over time, but also including artificial augmentations. And they train basically 3 different projection heads. So at the core, what they want to learn is this encoder F that would lead to this representation that we are interested in. But on top of that, then they have 3 different projectors that are trained to do different things. So the first one should be invariant to both seasonal and to artificial augmentations or transformations. The second one should only be invariant to seasonal changes, and the last one should only be invariant to artificial transformations. And the idea here would be that the model would then learn different features, some that are sensitive to changes over time, and some that are like invariant, so not sensitive over time. Because once this is pre-trained, we would discard everything from here. So all these H projector heads, they are removed, and we would only use the projection the representation after the encoder F. And this was quite promising. I think what's also interesting, so here you see the linear probing performance. That is when you freeze the encoder as a feature extractor and only add a linear head on it, or then the full fine-tuning experiment. And here you basically see how they improve from this GA-SSL towards SECO. Yeah, so I think that was interesting. What was also nice is they looked at two different sampling strategies. So one of them was just sampling uniformly over the landmass for the pre-training data, and the other one was sampling close to, here it's called Gaussian, but it means around urban regions, cities, big cities. And that seemed to improve the downstream performance on some urban tasks, which intuitively makes sense. So if you know what your downstream task is, you can actually improve your performance by choosing the right sampling strategy. I think that's the message here. Okay, and then this is the change detection result over here. So they could show that it actually matters quite a bit if we look at the overall F1 metric. That their approach now that basically has these two different projection heads, one that is sensitive over time, one that is not, that this is useful to later on fine-tune it for a change detection task. Okay, and then the last part would be to bring in multiple modalities, multiple sensors. And yeah, I also mentioned that on Tuesday, this masked image modeling is an alternative pre-training tasks. And the EO space, I think, is quite focused on mask modeling as well. And this is one of the earlier works that was trying to fuse different modalities in such a mask modeling framework. And it was later on also presented in this so-called 4M. I think it stands for massively multimodal, multitask, another M model. So it's an any-to-any approach again. So this model can then, was also able to handle text and a bunch of different rastered domains. And the whole idea was that this model can predict any modality from any input modality. And yeah, one can do a lot of stuff with this kind of model. And it was recently also taken and, for instance, trained on Earth observation data. So this is this TerraMind model that is also freely available, was developed by NASA and IBM. So yeah, a lot of these things are then taken from the computer vision ground level domain and then also explored in the Earth observation domain. And there are a few other papers that I want to point to, this DOFA and ANISAT. There are very recent papers that came out. And most of them, they really try to develop models that are that can generalize to different input modalities. And one key idea of these models is to basically tell the model in some way what modality comes in. For instance, for different optical sensors, they tell the model the wavelength, what this band actually has. So the model can learn some meaningful conditions here. Yeah, and then the question is how to benchmark all that. I already presented that slide on Tuesday. So there's GeoBench. There are a few other benchmarks coming up, but I think we're still a bit lacking like harmonized multimodal benchmarks. So I think that would be interesting if you have some application where you think this might be a good benchmark data set for these kind of pre-trained models. Might be a good idea to think about turning that into a benchmark data set for the machine learning community and prepare it in a way that people that do not have so much experience with handling geodata, that they can handle it with their standard tools. But yeah, so when it comes to very specific applications, those might be overlooked by the community, right? Because benchmarks somehow define what the community will aim for, so the broader community will try to improve these benchmarks. if you manage to establish your data set as a benchmark data set, you will get a lot of support in your application because the community will try to push performance on your data set. So this is just an interesting example from a paper that evaluated just a few pre-trained models. Here this SSL4EO trained on Sentinel-1 and 2, and then the SATLAS pre-train and some ImageNet pre-trained model on crop classification from Sentinel-2. And the most interesting thing, I guess, is that this SATLAS pre-train, it was pre-trained on Sentinel-2 images, like the downstream task is using, but it only performs just on par with a model that was pre-trained on ImageNet. So that's a bit a negative result, but I guess the main reason for this is that this SATLAS pre-train was trained on with a focus on urban tasks. So yeah, this was not really designed to map crops, I would say. So again, if we pre-train just on random or even the wrong locations, like really excluding basically all of the relevant pre-training locations, then this might not lead to good results. So we need a better selection. So ideally, we can inform this pre-training also with knowledge from our downstream task that we care about. And then, yeah, we maybe also need better pre-training strategies that are actually making use of Earth observation data. And that is maybe where you could come in when you have really good understanding of this raw data, you know how the physics work behind it, etc. That is probably where you can be very innovative and come up with new pre-training strategies that a general computer vision person might not think of. Okay, so this is, Tom mentioned it before, this was a summer school we organized last year in Copenhagen. It was focused on this self-supervised learning for Earth observation data, and we recorded all the talks, so you can find it on the website or this QR code. And there's also all the code available there if you want to get started with some of these pre-training strategies. So have a look there. And also what I can recommend, so we had Randall, who was at Meta, or just recently transitioned to the Brown University. He was the first author of this so-called cookbook of self-supervised learning. I can highly recommend to look at that. It's a very nice, it's an introduction, but it goes then into all the tricks and hacks that you need to make it work. So have a look at that. Okay, and with this, I guess I will conclude. Already a bit over time. So maybe just to summarize this, I think Earth observation, the metadata in our Earth observation data is great to design these better positives that are needed for self-supervised learning. And then, of course, the geolocation itself is just so important. And the selection, I think, is something that we need to make progress on, how to select the right pre-training data, because this is a bit different from all the pre-training stuff that just samples the internet. We sample our archive, right? And our archive is kind of, many sensors are quite systematically observing the Earth, and we have a bit more control over how we want to sample that data. So I think this is where the Earth observation community can play quite a bit of a role. Good. Yeah. Thanks so much.